Welcome to the lesson on section 12.12, Taylor polynomials. In this lesson, you'll learn how to use Taylor's inequality to determine the error in using an nth degree Taylor polynomial to estimate the sum of a Taylor series. The Lagrange error bound for Taylor polynomials is also known as Taylor's inequality. If R is the difference between the actual value of f of x and the value of the nth degree Taylor polynomial, Taylor's inequality says that there's some real number c for which the absolute value of r is less than or equal to the n plus first derivative of f calculated at c divided by n plus 1 factorial times the absolute value of x minus a raised to the n plus first power. This is very similar to the n plus first term of the Taylor series, except that we may not always use the same values in place of c and x. If this were truly the n plus first term, x and c would be the same number. When we use Taylor's inequality, we'll choose values for x and c from a given range of values to make the expression on the right as large as possible. In this example, I'll use a Taylor polynomial to estimate the value of e within 1/1000th of a unit. To estimate the value of e, I'll use the power series for the function e to the x, with x equal to 1. Here's the Maclaurin series for e to the x, and here's what it looks like when x is 1. According to Taylor's inequality, the error is bounded above by the n plus first derivative of f over n plus 1 factorial times the absolute value of x minus 0 to the n plus first power. That x minus 0 is because we're using the Maclaurin series, so our series is centered at a, which is 0. Since the series is centered at 0, and I'm evaluating for x equals 1, I can choose values between 0 and 1 for c and x in this expression. When we're not given a specific interval of x values, we'll choose between the center and the given x value. So in this problem, letting c equal 1 makes the n plus first derivative as large as possible, and letting x equal 1 makes the absolute value expression as large as possible. Note that the values you choose for x and c to make this expression as large as possible may not always be the same as each other, but they do happen to be the same in this example. According to the requirements of the problem, we need this error to be bounded by 1/1000th. I'll enter that into the y equals screen on my calculator and use a table to determine the smallest value of n for which the expression is less than or equal to 0.001. This occurs when n equals 6, so I would use the 6th degree Taylor polynomial to estimate the value of e within 1/1000th of the actual value. Let's check to see if that worked. At the top of the screen is the 6th degree Taylor polynomial for e to the x, evaluated at x equals 1. And underneath it is the value of e. These two values really are within less than 1/1000th of each other. Now I'll estimate the value of e to the point 2 within 3 decimal places of the actual value. In Taylor's inequality, I need to choose values between 0 and 0.2 for c and x to make the expression as large as possible. Choosing 0.2 for both x and c here, In order to keep the answer within 3 decimal places of the actual value, I need the error to be less than 0.0005. For example, 0.001 and 0.00149 would still round to the same number if we keep 3 decimal places. I'll enter the expression e to the 0.2 over x plus 1 factorial times 0.2 to the x plus 1 power, and use a table on my calculator to determine the smallest value of n for which this expression is less than 0.0005. This happens when x equals 3, so I would use the third degree Taylor polynomial. The third degree Taylor polynomial for e to the x when x is 0.2 is shown at the top of the screen. Notice that to the third decimal place, this polynomial has the same value as e to the 0.2. This concludes the lesson on section 12.12, Taylor polynomials.